Hi folks, we're going to take a look at the solution to page 157, number 17. So here's the question. So we've got a cylindrical can that has to hold 500 centimeters cubed of our liquid. Okay, and here they're giving us a constraint that the height has to be between 6 and 15 centimeters inclusive. Okay, so that gives us a hint that we're going to be working with a closed interval. Okay, how should the can be constructed so that a minimum amount of material will be used in the construction? Okay. Now, we've already done a similar problem, and we found that if there wasn't any restrictions, that we should get a can whose diameter is the same as its height. Okay, so we'll have to see if that's still the case here. Okay, so let's get rid of the textbook, draw ourselves a diagram, and solve this problem. Okay, so we're working with a cylinder. So even though we know cylinders well, not a bad idea to draw ourselves a diagram. Okay. And here we have the radius and we have the height. And what we're trying to minimize here is the amount of material. So we're working with the surface area, which for a cylinder where we're using all sides is 2 pi r squared plus 2 pi r h. So notice here, even though the first piece of information they gave me was something to do with the volume, I always write down what I'm trying to optimize first, which in this case here is the surface area. Okay, but again, we have a similar problem, and we see that we've got two variables. So that's where the volume is going to come into play. So before I forget anything, I look at all the units and I see everything's in centimeters or centimeters squared, or cubed, so I don't have to worry about changing any units. So the volume is 500, which of course for a cylinder is pi times the radius squared times h. Okay. Now this is where I have a decision to make. I have to decide which variable to isolate. So it's certainly much easier to isolate h. Problem is that the constraint they give me has to do with the height. They tell me that the height has to be between 6 and 15. Okay, so this might make me want to actually work in terms of height instead of radius, but I actually don't think it's worthwhile. Okay, I think it makes more sense to convert this into radius expressions, because there's no way I want to isolate r and then have to input it into this equation. Okay, so I think it's the investment is better the other way. So I'm still going to isolate h here, so 500 over pi r squared. So I'm going to input that into my equation, 2 pi r squared plus 2 pi r, and h now is 500 over pi r squared. And I end up with a fairly nice equation, 2 pi r squared. That goes, and so the only thing I'm left with is plus 1,000 over r. Okay, but again, I've got a function in terms of r. So here I know the height has to be between 6 and 15. Now one thing that I think is pretty reasonable is that as I increase the height, if I make it higher, okay, my radius is have to get smaller. If I make the height smaller, the radius is going to have to get bigger. Okay, so the minimum height should correspond with the maximum radius, and similarly for the maximum height. Okay, so here I'm just going to take this equation now, but I'm just going to use it to convert height values into radius values. So if I were to isolate r here, well, the pi h would go to the other side and I have to take the square root. So I'm going to have to determine the square root of 500 over pi times h, and let's start with 6, and I also have to determine the radius when the height is equal to 15. Okay, so I'm just going to calculate that here. Okay, so we have square root of 500 divided by 6 pi. Okay, so notice my use of lots of brackets. Okay, and here I get 5.15, so that should become the maximum radius value. So I'll put it there. Okay, and now let's calculate what should give me the minimum radius value, which is the square root 500 divided by 15 pi, and that gives me 3.26. Okay, so there's my constraint on the radius. Okay, so for me, doing these two quick calculations was better than having to work with this equation in terms of h. But of course, you might have chosen differently. So now we can take the derivative. So here we just end up with 4 pi r. Okay, this is like 1,000 times r to the negative 1. So the negative 1 comes down. So minus 1,000 r to the negative 2. Okay, so I'll just put that straight there. Okay, and of course, I have to determine when this is equal to 0. Multiply both sides of the equation by the lowest common denominator, which is r squared. So I end up with 4 pi r cubed minus 1,000 equals 0. And so r is going to be equal to the cube root of 1,000 over 4 pi. Okay. So now, question is does this radius, which represents my critical point, actually live inside this interval for which I'm interested in? So we're going to have to check that. So we have 1,000 divided by 4 pi. And to take the cube root, I'll just take exponent 1/3. Okay, and here we've got 4.3. And lo and behold, that does live within my interval. Okay. So again, I could show that this is an absolute minimum in that interval, or I could use the fact that I'm working with a closed interval and just test the surface area at these 3 points and see which one is small. So just to change things up a little, I'll do it that way. So I have to check a at 3.26. Okay, so let's get our calculator. I'll use this version of a. So we've got 2 times pi times 3.26 squared plus 1,000 divided by 3.26, and I end up with 373.5. Okay, let's check the area at our critical point, 4.3. Okay, so here 2 times pi times 4.3 squared plus 1,000 divided by 4.3, and I get 348.7, so that's smaller. And let's see the other endpoint. I think we know exactly where this is going to go, but let's just do our due diligence here. So here we've got 2 times pi times 5.15 squared plus 1,000 divided by 5.15. Whoops, that should be 5.15. Okay, and we have, so I'm actually getting a smaller number here. I'm a little suspicious about that, so I'm just going to check that again to make sure I did not make a mistake. Okay, so 2 times pi times 5.15 squared, okay, plus 1,000 divided by 5.15, and there we go. So I think I must have, when I made that change, I must have made a little mistake. Okay, so since I was expecting this to be a minimum, that always helps. Okay, and so there we go. This is going to give us our minimum value. Okay, and let's see what they're actually asking me for. It says, how should the can be constructed? Okay, so for me, that essentially asks for the dimensions. Okay, when we say how it's going to be constructed. So our final answer here, well, we know that our radius is going to be 4.3 centimeters. Now, since it's occurring at our critical point, we should expect this to be 2 times as big. But let's put it back into our relationship for h. So 500 divided by pi times 4.3 squared. And I expect to get 8.6, but let's see what happens. 500 divided by pi times 4.3 squared. And lo and behold, we do get 8.6 centimeters as expected. Okay, so just a quick recap. Okay, the only difference between this problem and some other ones is that we weren't given the information in terms of radius, it was given in terms of height. So we had to make a decision. Do we solve this problem using height as our variable, or do we still keep radius and then have to do these quick changes in values? Okay, so up to you to decide. That's it for this one.